Good morning, AOBI. This is Mr. Dunning. Stand by. I have a math lesson for you. In our previous lessons, we looked at ellipses that got squished that way. Expanded on the x-axis, shrunk on the y-axis. Today, we're going to look at ellipses that get squished this way. Shrink on the x-axis, grow on the y-axis. And we're going to see the similarities and a few differences and how to handle those. So stand by. We're going to take a look. And you are going to gain an understanding. In a previous lesson, you learned that a cutting plane perpendicular, the axis of the cone, gives us a circle. When that cutting plane is at an angle to the cone, it gives us an ellipse. But the way in which the plane tilts makes a difference. If it's tilted along the x-axis, the cone gives an image that grows on the x-axis. If it's tilted on the y-axis, then the image grows on the y-axis. So it takes us back to cones and cutting planes. The image on the axis will be an ellipse, but the angle of the cutting plane makes a difference. If it's cutting extended x, then the ellipse is extended x. If, on the other hand, it's cutting with an extended y, then the ellipse grows on the y-axis. So the cutting plane makes a difference. The direction of tilt makes a difference. The equation of the cone stays the same. The image of the cone is going to change, and we're going to look right now at the equations that result where B is bigger than A. In this equation, B and B squared are bigger than A and A squared. This is your clue that the cone is getting squished this way and growing that way. If the B is bigger than the A, the squish is this, and the growth is up the y-axis. Let's see how this plays out. In our picture, A is 2, and B is 3. And there's our ellipse. A is 2, B is 3. You're saying, well, wait a second, the ellipse is vertical. Yes, it is. That's because B is bigger than A. Graphing these is just as easy as before. Piece of cake. Get the right edge, the left edge, the top, and the bottom. Sketch your ellipse. But there's a caution here. When you go to find ellipticity, the formula for ellipticity needs a little tiny bit of doctoring, because now A squared minus B squared will give you a negative here, and we can fix that easily. So we're going to take the square root of the absolute value. Of A squared minus B squared. But our major axis is vertical, and so this piece has to go here. That's the ellipticity of a vertical stretch. Let's do another couple or three of these so that you can get the idea of how this works. In this example, B and B squared are much bigger than A and A squared. So we know that the stretch is vertical. The squish It's that way. So we're going to go 3 over to the right, 3 over to the left, 5 up, and 5 down. Now we can sketch our ellipse. And there it is. See this beautiful egg? Now, let's talk about this thing. Ellipticity. When I want to take the difference of two numbers, if I want to take this one away from this one, that's the difference right there. Pay no mind to this thing. If I want to take this one away from this one, guess what? That is still the difference. The only difference between the two differences is the sign. And we solve that with the absolute value under the radical. B squared is 25. 9 minus 25 is minus 16. But the absolute value of minus 16 is 16. Square root of 16 is 4. B is 5. So in this ellipse, the ellipticity is 4/5 or 0.8. Now, this number here, 4, still identifies the location of our foci. 4 up and 4 down. But remember, if the squish is this and the growth is on the y-axis, the foci are on the y-axis also. Piece of cake. All has to do with the orientation of the cutting plane. Perpendicular to the axis of the cone, you get a circle. Tilt on the x, you get a growth on x. Tilt on the y, you get a growth on y. The angle of the cutting plane makes a difference, and it shows up here in the equation. One more example. Here, you can see that the b and b squared much bigger than the a and the a squared. Still not a problem to graph this. A squared is 4, a is 2, so we're going to go over 2 to the right, over 2 to the left. Those are the edges on the x-axis, the ends of A. B is going to be 4, so we're going to go up 4 and down 4. Now we can sketch our ellipse. And look at that beautiful egg. There's our ellipse. Ends on the x-axis, ends on the y-axis. Boom, done. No change. But when we look at ellipticity, we have to remember this absolute value. Our next stop is going to take us back to cones and cutting planes and this ellipticity thing, and it's going to be a segue into what's coming for the rest of the school year. Stand by. Now let's talk about this ellipticity thing. You know that if the cutting plane is perpendicular to the axis, the ellipticity is 0, we have a circle. That's the green cut. And in an ellipse, the ellipticity has to be bigger than 0 and smaller than 1. But what happens if the ellipticity is 1? What's going on here? And the answer is the cutting plane is now parallel to an edge of the cone. And that gives us an ellipticity of 1. Ellipticity of 1 gives us a parabola. Yeah. And that's our next step. For the rest of the school year, we are going to be examining parabolas. And we're going to learn a whole big bunch about them. As always, you've been a fantastic audience. I hope you have a wonderful Monday, and we'll see you tomorrow.